things that are just moving, standing still, or moving in a straight line are not so interesting in nature, right? There are not very many things that we see that are just standing still. Standing still doesn't have motion. If we study motion, it's not interesting to us in that category. It may be very interesting to somebody else studying it because of its material properties. If it's moving in a straight line forever, it's kind of boring. I mean, we know exactly where it's going to be. It's very simple to know where it's going to be. When does it become interesting and challenging? If it's just moving at a constant speed, we now know how to measure, let's say, the speed that it's moving at. Obviously, we know the speed, we know how much distance there is between us and it, we know how much time it's going to take. Very, very simple problem. Most problems in nature are not like it. Most problems in nature have things moving more complicated than this. All right? The simplest complicated way is if it's speeding up or slowing down. It's still moving in a straight line. It's more complicated if it's moving in a circle or moving in other ways and so on. Let's take the simplest case. It's moving and then something pushes it. Or it's standing still and something pushes it. It's moving and something stops it. Okay? What's happening is the motion is changing. Changing motion is more challenging, but more interesting because most things are moving in a changing way rather than just like that. Okay? Even meteors are not moving quite like that because as they get closer to a solar system, they start speeding up and changing direction. What do you think will determine how much it'll slow down or how much it'll speed up? What factor? Let's say, will it be the name that you call the object? If I call this a ruler, if I call it a meter, will it move differently? Okay, how do we know? How do you know? Okay, but how do you know that it's not, that what if I call it something else, it doesn't matter?
Mass.
No, but how do I know? Let's say if I call this a meter stick or a ruler stick, how do I know that it's not going to affect how it moves? I try it. I say, well, let me call it a meter stick. I push it, I see how it goes. I try it. Let me call it a meter stick, and I push it. My experience is that it doesn't matter what I call it. Okay? If I paint it green, will it make a difference? Well, it depends. The extra weight of the paint might do it, but other than that, right? So the color doesn't matter. The name doesn't matter. What matters? Let's say if I change the shape. Okay, if I change the shape, it'll matter. Okay, anything else? If I change the, what? If I change the weight? Okay, what else? Anything else? Okay, okay, that's true if I change the surface on the bottom. That's the, we already gave that term, we call that friction. That's true. Okay, but let's say about the object itself. Let's say we're in space, okay? Let's say we're out in space, so there's no friction. Okay? So now what things determine how much is going to move as a result of the force? So we said the shape and the weight. What else? Anything else? Pardon me? Okay. Why would the shape make a difference? And why would we think the shape would make a difference?
Surface area? Would that count?
Okay, so why would that make a difference?
I'm not sure.
Well,
Even should.
This would be obsolete in space. But as something's pushed, there's a force coming from the other direction. So,
Well, I'm sorry, say it again. There's a force.
if something's going in one direction, there's resistance coming.
Why is there resistance from when?
Why?
Where is resistance? What's resisting?
The air.
No, but around the space.
No, I'm saying
Well, let's say in space. Around the space, there's no air.
It wouldn't matter.
So you say the shape matters, maybe, but you're not sure. You say the shape won't matter.
Wouldn't think so.
Okay. Anybody else? Maybe that on the back. Want to contribute something? What do you think?
Well, in space, man, I don't think that any shapes or weight or
Okay. All right. So you don't think so. Now, how would we find an answer to that rather than speculate? We have to experiment. We have to go out in space and try different shapes. Okay? A cheaper and simpler way that we can use to experiment that's not quite as accurate maybe or reliable is to try an experiment on Earth. First of all, we can take a chamber and evacuate the air and say, well, how does it move without air and so on and so forth, right? But then we still have gravity. Well, we can reduce the effect of gravity by maybe putting it in water, but then it's certainly going to not move very much. So we can put it on ice. You can do all kinds of experiments in the lab that simulate space one way or another, taking away one thing or another, the gravity pull or the friction or something like that, but just one at a time. Now, we can also try to think, well, what is it that does, why is it that shape does affect? Why would shape affect motion? I mean, why should it be more important than, let's say, the color, if I paint it green? I mean, why is shape more important than color? So in other words, what we do is take objects of different shapes, right, but the same mass. If they're different shapes and different mass and they fall differently, what's the problem? Pardon me? Let's say that we take two objects and they have a different mass and a different shape and we see that they fall differently. What can we conclude from that? Well, how do we know? Maybe it's the mass. Maybe it's the, if you have a different mass and a different shape. Ah, okay. Well, I'm saying if you take two objects of different mass and different shape and different color, and you drop them and they fall differently, what can you learn from that? Not very much. Well, how do you devise a better experiment?
You make sure everything is the same except for one thing you're trying to test.
Everything should be the same except for one thing, so that you know that one characteristic actually affects it. Right? Makes sense. So what we do is we take two objects of the same mass and different shape. Okay? A simple way of doing that, take two pieces of paper, okay? Same, well, just put up the same thing to shoot it. But, all right, how would we give this a different shape?
Crumple one.
Okay? Do they have the same mass, the same weight,
Yeah.
Okay. Simple experiment. What did we find? Shape is important. Okay. Why is the shape important? Okay. If we see this as like kind of going like this. What's the, just from our experience, what do we know? When we run, what do we feel? We feel like a wind. Right? Where's that wind suddenly coming from? It wasn't the wind before. So we say it's the air that we're displacing, we're moving air away as we cut through it, it's pushing against us, right? Alright? So shape is important. But if there were no air, now we do again a radical leap of the imagination. We say, let's take away the air. What will happen? Well, we don't know. We have to do it. Maybe there's something else. Maybe even when there's no air, there's some other reason why shape is important. So we can't really know that without doing an experiment, right? But you can do these experiments on Earth in a vacuum chamber, right? You can't get rid of the gravity, you can get rid of the air. And if you do that, you'll find that these fall at the same speed. So you solve the mystery, you find shape is important. The reason shape is important is because of air resistance. In space, where there's no air, if you push them, now let's say I'm going to space, and I stand there in space, empty space, and I let go. What's going to happen? They'll fall at the same speed? What do you expect? I'm out in space, let's say, 20 trillion miles away from anywhere. I let these go. What happens? Nothing. They just hang there. Because there's nowhere to fall to. Falling is only when you're near some mass and it's pulling you. So that's what we call falling. Right? If you're not near any mass, if you're very, 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 very far away, there's nothing pulling you. There's no reason to go this way or that way or that way or that, because there's nothing anywhere. So it just stays there. So, but again, shape is not important. Obviously, they're doing the same thing. Okay. All right. So now we discovered, or at least imagined, okay, some important things. Shape doesn't matter. The color doesn't matter. The name doesn't matter. So what does matter? And again, on Earth, it does matter if there's air. Okay, but we're trying to come up with abstract general laws that have to do with the motion itself, not with the complicating factors because we're on planet Earth and because there's air and so on and so forth. Okay, so what does matter? Mass? Okay, what is mass? Volume? Volume and weight. Okay, what is volume? Volume has to do, I think, kind of with shape, right? I can take this paper and, build a little kind of cube out of it, right? Right, like a paper cube, whatever. This has more volume than the page did before, doesn't it? Do you think in space it'll make a difference one way or the other? What is your intuition now? It might. Maybe maybe volume is important. But we can do the same experiment in Earth without air, and let's say drop this and the flat page and the crumpled one. They have different volumes, and we'll find, in fact, that they all follow the same. So volume itself is not important. Okay, so what might be important?
Wait.
Weight. Okay, what is weight? Sorry?
We gotta do it for an object.
I guess on Earth we would measure the amount of gravity.
Yeah.
Okay, the amount of gravity.
On Earth, right?
Okay, we'll get to that later, what it is exactly. Let's say if I'm out in space,
Isn't there a closer thing in
if I'm close to the Earth, they'll be equal to the Earth. If I'm close to the Sun, they'll be equal to the Sun. If I'm far away from anything, if I look around, I see nothing. There's no stars, there's no planets, there's no nothing. I'm just out in space, if there is such a thing, which there isn't, because we'll always be able to see some galaxies far away, but if you're far, far enough from any galaxy, the tug on you will be so small that it will be imperceptible. So we'll ignore it. We'll assume that this is not there. We'll make up this hypothetical empty space where you're so far, you don't even see, there's nothing, there's no lights, there's nothing. Okay? Far from anything. And again, this is a leap of imagination because we've never been there. We don't know if such a thing actually exists. Right? But we're extrapolating from what we kind of know to something a little further to see if we can kind of come up with something very general that doesn't depend on the particular instances of, like, okay, here we're on Earth, so there's air. You know, forget about that. Okay, so we're near, however far we can go with our rockets, we'll always be near the sun. Let's forget it. Let's try to come up with something more general than that's bounded just by the particular details of our experience, right? You know, the way we know it. Okay? So, and we may be wrong. It's just, maybe we're extrapolating, we're imagining, and we're doing all this stuff, and it's wrong. You have to test it. It's true. And if you can never test it, then you don't know. Okay, so we're far, far away. Shape doesn't matter, etc. So, what is there weight? Does the object have weight? It doesn't have weight, because weight is the gravity pull pulling for something. That's what weight is. So it has no weight. So what does that mean? Let's say you have an elephant and a ping pong ball out in space, and me. And then push on both of them with the same force. What will happen? They'll move at the same speed. Okay. Now let's say the elephant takes its leg and bends it, and I bend my arm, and we push against each other like this. What'll happen?
The elephant will go twice as, will go farther, right? Than if the ping pong ball.
I don't know. That's what we're trying to figure. What makes sense? I mean, if the elephant and I push against each other, will I move? Will he move? Will we both move? Will we both move the same way? But there's no weight.
No, it has more power. The
What
elephant's
does that
more
mean?
dense.
No, but we're exerting the same amount of force.
But the elephant's more dense. than
Okay, we're
ping
exerting
pong
the same
ball.
amount of force against each other. Okay? We agree. We push against each other the same amount. Okay, so if we both push on the elephant, so if I push on the ping pong ball, we should also both drift away from each other.
No,
Why not?
because there's no density in the ping pong ball. It's not going to push equally.
But why? So you're saying there's such a thing as density, and that determines how it's going to work? If the ping pong ball has a little like a plastic thing that you bend, like on an arm,
Yeah.
right? A little tiny thread, like, right? And I bend my arm, and it bends its arm, kind of, we push again, just like me and the elephant.
Yeah.
I mean, me and the elephant is the same like the ping pong ball and me, right? So we'll both move off like that. I mean, when I push on the elephant, imagine now that this arm, I glue my arm to the elephant. Okay? So the arm is basically belongs to the elephant, belongs to me. And then I flex it like this, and then I glue it. Right? And then I extend my arm. A wooden bracket with a hinge between me and the elephant. And then I extend the arm, like I straighten it like that, so it pushes against both. Right? right? That's what's happening, right? Pushing against the elephant, just on the arm. What will happen? And I can do the same thing between me and the ping pong ball. Will the ping pong ball move and me stationary? Will we both move off the same? Will me and the elephant move the same? In other words, is there some property that has to do with, we don't even have a term for it. It's not volume, right? We saw that volume is misleading, right? We take this piece of paper and make it, right? I can take a piece of paper and make it as big as the elephant, and you know it's not the same, right? It's not weight because they don't have weight. So there's something else fundamental about objects that has to do with resistance to motion that intuitively we feel, we don't know, that even in space where there's no gravity, it will resist the motion more. It's an assumption. We don't know, but we have to test it. Okay? And it's not weight, because there's no weight. And it's not shape, and it's not. So it's something. Now I'll give it a name, but giving it a name doesn't explain what it is. It's called mass. That doesn't mean, oh, now I know what it is. I just gave it a name to that thing which we feel intuitively. There's some property that everything has that when you have more of it, what happens? When you have more of it, you resist motion more. Okay? And because the elephant has more of it than I do, if I push on the elephant, what I more expect to see is I'll move back a lot, and the elephant might move a little bit. If I push on the ping pong ball, the ball will move a lot, and maybe I'll move a little bit. That's more in line with our intuition, which doesn't mean that it's correct. All right? How would you test something like that? Let's say on Earth. Well, one of the ways you can test it is try to simulate the situation in space. Now, the difference between me and the elephant is not affected so much by whether there's air or not. That's our intuition also. We can reduce the air more and more, but we know that whether I'm going to move, the elephant's going to move, there's nothing really to do with the air resistance. I mean, we'll both be affected by the air resistance, but that's not what determines the difference. What's determining the difference is the weight. Well, why is the weight so important? Why, if I push against something so heavy, doesn't it move? There's two factors. One is the friction, right? It's planted firmly on the earth, and when I try to push it, it's very difficult to push. It's squeezing against the earth so much, it's very hard to push. Okay? So what do I do? I put the elephant on roller skates. Okay? Rollerblades or ice skates, even better. Put it on ice skates on the ice. Okay? And I'm on ice skates also. Now, neither of us really has that much friction. If you push on it, it'll move. So you can test it and see. Do we both move off? I do the same thing with the ping pong ball, with a piece of paper, whatever. And I find that, in fact, it's true that the elephant has more of that whatever, and I have less of it, and the ping pong ball has even less. And then we can do an experiment. We take 2 ping pong balls or 3 ping pong balls. We find that 3 ping pong balls reacts a lot less, or has more of that than 1 ping pong ball. And we can do experiments and find it has 3 times as much. So we can start getting a measure of it. We don't know yet what it is. We just gave it a name. We call it mass. But then we can do it with atoms, and we find that 1 atom, 2 atoms are the same thing, and 1 atom, right? And the 2 atoms has twice as much resistance as the 1 atom. So we don't even need a further definition. We call it mass, and we say it's a property of stuff, things, all right? And if there's 2 atoms, then it has twice as much. Then we take atoms that have different properties, it's a different amount of protons and neutrons and so on. The more they have of this. So we can say, well, let's define it not in terms of atoms, we'll define it in terms of protons. And protons have this property of resistance to motion, and if you have 10 protons, it has 10 times as much, let's say, as 1 proton. And we call that property mass. We're still trying to know what it is. It just is. It is. That's all. Another effect of mass is we find that things that have more mass also weigh more when they're on the Earth. All right? But that has nothing to do with the mass. It has to do with gravity. They're 2 entirely different things that we kind of intuitively sometimes blur the distinction between them. Right? You kind of think that mass and weight are the same. Nothing to do with each other. One is resistance to motion that would be even in outer space where there's absolutely no gravity. There's nothing to do with gravity at all. And an entirely different phenomenon, which is gravity, which seems to affect it. The heavier you are, the more mass you have, which would mean that the more resistance there would be to motion in space, the more heavy you feel on Earth. Okay. Remember we spoke about weight and mass, and we said that they're not the same thing? Weight is what happens to a mass in a field of gravity, it has weight. What is weight? Weight is the force of gravity acting on something. When we experience it ourselves, we call it our weight. Right? We feel we have weight. In other words, we feel gravity acting on us. Okay? But remember we spoke about if you take an object far out into outer space where there's no body out there, there's nothing else out there, so there's no gravitational interaction between it and anything else, then it will have mass. And we actually spoke about that. It wasn't entirely obvious to everybody, it wasn't intuitive, that an elephant and a ping pong ball would react differently if you push it in outer space. But they do react differently. Objects have mass. The more massive they are, the less acceleration they will have for a given amount of force, even if there's no gravity. It's entirely unrelated to gravity. The property of mass is entirely unrelated to gravity. Take something that has twice as, take one stone and take two, or one, let's say, brick, and then two bricks that are, each brick is identical to this one, so this one has twice as much mass as this one. If you push on with the same force on both of these, right, this one will accelerate with half the acceleration because it has twice as much mass, even if there's absolutely no gravity acting. Okay? And of course there is always some gravity because if you have two particles, every two particles in the brick are interacting with each other with gravity. But in other words, there's no major source of gravity. There's no sun, there's no star, there's no planet or anything else. Okay? So mass is a property of any object, and it's related also to energy through Einstein's famous formula, which maybe at the end of next semester we would discuss. But basically, any object has mass, and if you're in a gravitational field, in other words, if you're near some other object which has mass, the two masses will attract each other. That's something entirely different. That's called the force of gravity. Okay, so don't get confused between mass and weight, which is directly related to the force of gravity. So we have a property, we'll just write n for mass, okay? And we'll call that n with a little I there. That little I means inertial mass. Why inertial mass? Because we said Galileo came up with this idea of inertia, that things don't move unless you push it, and if you move it, it'll continue to move forever, and so on. That property of resisting change in motion, either just standing still, or if it's moving, it continues to move, that's this mass, that's this property that we're talking about, right? If you want to push it, that's what you have to overcome. And once you overcame it, just continues going on. All right? It has nothing to do with gravity. All right? Inertial mass. So we know now, or we theorize that inertial mass is a property that's relevant as opposed to shape, color, name, etc.